So, I've been thinking about the future of tech, not just the next gadget or app, but the very core materials that make all of our digital lives possible. It's easy to get caught up in the excitement of new phones or laptops, but beneath every screen and circuit is a story of innovation that's been quietly unfolding for decades. For decades, silicon has been the foundation of every smart device you own. From the first bulky computers to the sleek smartphones in our pockets, silicon has powered the digital revolution, acting as the backbone of modern electronics. But what if I told you its reign might be ending? Imagine a world where the material that defined an entire era of technology is finally being replaced. It sounds wild, almost like science fiction, but breakthroughs are happening right now, right under our noses. Researchers are racing to find the next big leap, and the pace of discovery is accelerating. A team at Penn State has built a fully functional computer processor with zero silicon. That's right, no silicon at all. This is a milestone that could change the entire landscape of computing. Instead, they used materials just one atom thick, so-called two-dimensional materials. These are substances so thin, they're almost unimaginable, yet they have properties that could revolutionize electronics. This isn't just a lab trick or a proof of concept, it's a fundamental shift in how we build electronics. It's the first real glimpse of a future where our devices are lighter, faster, and more energy efficient than ever before. Your current devices won't vanish overnight, but we're pushing silicon to its absolute limits. As chips get smaller and more powerful, we're running into physical barriers that silicon just can't overcome. The Penn State project is proof that a new path is possible, one that could make tech smaller, faster, and more powerful. Imagine computers that are not only more capable, but also more sustainable and efficient. We're at a crossroads. For over 50 years, computing has meant silicon, but now, a new chapter is being written. The rules of the game are changing and the possibilities are endless. In this video, we'll explore why silicon dominated for so long, why it's reaching its limits, and how 2D materials could change everything we know about technology. We'll look at the science, the challenges, and the potential impact on our daily lives. We'll break down the Penn State breakthrough, the hurdles that still need to be overcome, and what a future powered by atom-thin computers might look like. Imagine devices that are not only faster, but also flexible, transparent, and even wearable in ways we've never seen before. This could redefine everything we know about tech. The way we work, communicate, and even think about information could be transformed by these new materials. The story of computing is about to get a radical new twist. Let's dive in and see how the next era of technology is being built, one atom at a time. The end of the silicon era? Maybe not today, but the future is being built, one atom at a time. The seeds of change have been planted, and the next generation of tech is already taking shape. Welcome to the next frontier. Let's see what's possible and imagine together the world we're about to create. Why did silicon become the backbone of our digital world? It's a semiconductor, meaning it can switch between conducting and insulating electricity. Perfect for building transistors, the on-off switches of computing. Silicon is also abundant and cheap, literally found in sand. When exposed to oxygen, it forms silicon dioxide, a natural insulator that keeps transistors from interfering with each other. This unique combo made silicon unbeatable for decades. Moore's law, doubling transistors every 2 years, drove explosive progress. That's why your phone today outpowers supercomputers from the 1980s. Silicon isn't just a part, it's the foundation of the modern world. If silicon is so great, why look for something new? We're hitting a wall, literally. As transistors shrink to atomic scales, quantum effects like electron leakage become a huge problem. This wastes energy, generates heat, and makes the on-off switch unreliable. Engineers have tried clever fixes like 3D transistor designs, but these are just temporary solutions. Silicon can't be made much thinner and still work. We've squeezed out nearly all its potential. To keep advancing, we need materials that work at the nanoscale, something fundamentally different. That's where 2D materials come in. They're not just an upgrade, they're a paradigm shift. The silicon wall is real, and it's time to look beyond it. The future of tech depends on finding a new recipe. 2D materials might be the answer. Let's see why. So what are 2D materials? Imagine peeling a single atom-thin layer from a block of graphite. That's graphene, the most famous 2D material. But there are hundreds more, each with unique properties: insulators, superconductors, and crucially, semiconductors. Transition metal dichalcogenides like molybdenum disulfide, MoS2, are the 2D equivalent of silicon. Their atomic thinness solves the leakage problem, no more electrons tunneling through. 2D transistors can be smaller, more energy efficient, and generate less heat. They're also flexible and transparent. Imagine bendable processors or displays built into Windows. 2D materials aren't just a silicon replacement, they open doors to tech we can barely imagine. They're a new toolbox for engineers, with properties silicon could only dream of. The possibilities are endless. This is why the world is so excited. 2D materials could change everything. Let's see how. Now, let's talk about the Penn State breakthrough. Building a single 2D transistor was already impressive, but a whole processor? That's next level. The team used two 2D materials, MOS2 for transistors and tungsten diselenide, WSE2 for memory. They created both N-type and P-type transistors, essential for modern logic circuits. For memory, they built SRAM cells using WSE2. By combining these on one chip, they made a complete integrated system. The result? A 16-bit RISC-V processor with over 1,000 2D transistors and working memory. They ran real programs on it, proving it's not just a science project but a real programmable computer. This is the world's first fully 2D material-based microprocessor. It's a true milestone. The age of atom-thin computing has officially begun. What does this 2D computer look like? It's tiny, but the achievement is huge. The chip combines logic and memory, something never done before with only 2D materials. Using MOS2 for logic and WSE2 for memory, they built a 16-bit RISC-V processor with 1,364 transistors. It's not billions like modern chips, but it's a giant leap for 2D tech. They loaded simple programs, including a basic AI classifier, and it worked. This isn't just a lab curiosity, it's a real, programmable computer built from atom-thin materials. For the first time, we've moved beyond silicon to build a working processor from the ground up. It's the hello world moment for 2D electronics. The future just got a lot more interesting. As groundbreaking as this achievement is, it's important to recognize that there are some significant challenges ahead on the road to making this technology practical and widespread. Every major leap in science comes with its own set of obstacles, and this is no exception. For starters, the current prototype operates at just 2 kHz. To put that in perspective, that's millions of times slower than the processor inside your smartphone or laptop. It's a huge gap, and it highlights just how early we are in this journey. This sluggish speed is mainly due to the experimental nature of the fabrication process and the relatively large size of the transistors being used right now. These are not yet optimized for speed or efficiency. Then there's the challenge of mass production. Creating a single chip in a controlled lab environment is already a complex task, but scaling up to manufacture millions or even billions of these chips reliably and cost-effectively is an entirely different challenge that requires new tools, processes, and expertise. Another major hurdle is growing perfect, large-scale sheets of 2D materials and then patterning them with extreme precision. This is a delicate process, and mastering it at industrial scales could take years of research and development. There's also the issue of contact resistance, essentially how to efficiently get electricity in and out of these atom-thin materials. This remains a major bottleneck, limiting performance and reliability. These are tough engineering problems, and they won't be solved overnight. But history shows us that with enough creativity and persistence, even the most daunting technical challenges can be overcome. Think of this moment like the Wright brothers' first flight, short, slow, and far from perfect, but a powerful proof that the impossible is possible. It's a small step that opens the door to a whole new era. The underlying concept is sound, and now the real work begins, refining the technology, improving performance, and figuring out how to scale it up for real-world use. The journey from laboratory curiosity to industry standard will be long and full of unexpected twists and turns. It will require patience, collaboration, and relentless innovation. But the first step has been taken, and that's always the hardest part. Every great technology starts with a single breakthrough. The future is wide open, and the possibilities are limited only by our imagination and determination. Imagine a world where 2D electronics are everywhere. Devices could be nearly invisible, running for weeks on a tiny battery. Medical sensors inside your body, smart dust monitoring forests, or rollable phones in your pocket. Flexible, stretchable electronics could turn clothing into computers or make entire car dashboards interactive. The line between objects and computers would blur. Data centers could become ultra-efficient, slashing energy use and environmental impact. Supercomputers and AI could leap forward without the energy cost. Ubiquitous computing, processing power in everything, everywhere, would become reality. This isn't just about thinner devices, it's about a world where technology is seamlessly woven into our lives. The Penn State chip is just the first step. The future could be beyond anything we've imagined, and it's closer than you think. July 1st, 2025, may be the dawn of a new era in computing. As the sun rises over our cities, a new chapter in technology quietly begins, promising to reshape the world as we know it. We've gone from the bulky vacuum tubes of the past to the sleek, powerful silicon chips that fueled the digital revolution, and now, to the edge of possibility with atom-thin materials that could redefine what computers can be. The Penn State processor is more than just a scientific achievement. It's proof that we can build computers without relying on silicon, opening doors to entirely new ways of thinking about hardware. This breakthrough will ignite a global wave of research and innovation, as scientists and engineers from every corner of the world race to explore the potential of these new materials. Of course, progress won't be smooth. There will be unexpected setbacks, technical challenges, and surprising discoveries along the way. Every leap forward comes with its own hurdles. But the prototype is real, and the race to develop the next generation of computers is officially underway. The excitement in the labs is palpable. Right now, the next chapter in technology is being written by passionate people, scientists, engineers, and dreamers, pushing the boundaries of what's possible, experimenting with new ideas, and building the future piece by piece. The Silicon era built the foundation of our modern world, powering everything from smartphones to supercomputers. But now, something entirely new is on the horizon, ready to take us even further. Imagine technology that's thinner, more flexible, and more efficient than ever before. Devices that can bend, stretch, and seamlessly integrate into our daily lives in ways we've only dreamed of. We don't know exactly what the future holds, but the possibilities are as thrilling as they are limitless. Each new discovery brings us closer to a world we can barely imagine today. The age of silicon isn't over yet, but for the first time, we can truly glimpse what might come after, an era shaped by materials and ideas that were once science fiction. And I can't wait to see what we build next, as we step boldly beyond the silicon horizon into a future limited only by our imagination.